Thanks very much. So thanks everyone for coming this evening. It's really big turnout in person and online, so we really appreciate that. So I'm going to talk in the next few minutes. I feel like I should be like singing karaoke with this, this mic. But I'm going to be talking about speeding up Python with financial use cases. I'm one of the co-founders of Turnleaf Analytics alongside Alexander Denef, and we use a lot of Python in terms of what we do. We do inflation forecasting. But one of the issues with Python is it's not the fastest language, as I'm sure many people here are aware. So often you need to kind of have a few tips and tricks to kind of speed it up. Okay. So this is just a bit more about me. So saying a bit more about Turnleaf Analytics, and also I'm one of the co-founders of Telesians as well. So as a result of what we do, we use a lot of machine learning to create inflation forecasts. We ingest large amounts of data. If you want to do sensitivity analysis, it can be very computationally intensive, but you want the results fast. So we're continually thinking about how to speed up our stack, loading in terms of loading the data, crunching the data, and so on. So we're going to look at a few different approaches to speeding up Python code. Depending on time, actually, because I don't want to keep you waiting too much. But we're going to talk a bit about Dask and Vaex, which are kind of substitutes of pandas, and we're going to give a few examples with number crunching tick data. We'll talk a bit about polars, not too much, and then we'll talk about Cython and in particular number later on. And if we get a bit of time at the end, we'll talk about a specific use case speeding up the cumulative distribution function as well for the normal distribution. So we're going to use pandas as our benchmark here. So in a couple of these examples, I'll look at processing high frequency tick data on Eurodollar. So this is irregularly spaced tick data. We're going to use around 15 years of data. So as usual, if you want to use pandas, you need to import it. And our calculation is pretty simple. So to begin with, we're going to just read this file from disk. I'm not going to run it on the laptop here because my laptop will probably crash. I've pre-run this earlier on. And then we're going to calculate the mid price, the spread between the bid and the ask, essentially. And we're going to calculate the mean of all these various columns. So nothing too complicated here. But I want to have some sort of general calculation, which you typically do when you're working with high frequency tick data. So this relatively simple calculation using pandas on the machine that I benchmarked on, which is a pretty powerful machine. It has 128 gigabytes of RAM. It's i9 machine, I think 9th generation. So it's fairly fast. It takes around 1 minute on that machine. Let's talk about using Dask instead to do this computation. So Dask has several different backends. It has a synchronous backend, threaded, which is more for IO intensive operations, multi-processing, which is when you have more compute intensive. And one of the things that Dask has is a Dask data frame. And essentially a Dask data frame is a bunch of pandas data frames underneath. That's essentially what a Dask data frame is. So it allows us to also do compute on data sets which are bigger than memory. With pandas, you can't do that unless you batch it. With Dask, however, you can work with data sets which are larger than your RAM will allow. So we're going to import Dask. We're going to import the Dask data frame. And rather than loading one very large file of tick data, and in general, you probably shouldn't store all your tick data in one very large file. It's not a great idea. I've instead stored the data in a bunch of Parquet files for each year. You could also do it for each month as well. So when we read Parquet, we can read in the Eurodollar files, and we put this wildcard symbol here. And then we now do the mean, and then we also do the sum as well. I guess the sum is probably not that useful. It's just more doing a computation, essentially. So what we do is with Dask, it uses lazy evaluation. So that means when you push calculations to the computation graph for Dask, it won't necessarily calculate them instantly. So what happens is you keep on adding calculations, and eventually you trigger it using this compute command, and Dask will essentially optimize the construction of the computation graph. So if you look here, when we're doing the mean and the sum, a lot of those computations will be shared between the mean and also the sum. So it's going to optimize it so it doesn't do those twice. So if we use Dask to do this computation, it's around half the time, that 27 seconds instead of 1 minute. So Vaex is a kind of a similar library to Dask, and it shares some of the functionality that Dask data frames has. And one of those shared bits of functionality is that Vaex allows you to work on data sets which are larger than memory. So that's kind of shared. And it ends up being a lot more efficient than Pandas, which has quite a bit of overhead compared to using NumPy. Vaex also works on Windows and Linux. We heard Ryan speaking about KDB, and that's designed for high-frequency columnar data like time series. Vaex, I don't think it's not as fast as KDB, but some of the techniques it's used are kind of similar in terms of memory mapping from disk. This contrasts to something like Pandas, where you have to load everything up into memory first before you're doing the computation. So that's a key difference between Pandas and Vaex. So what we're going to do is we're going to use Vaex here. So we're basically going to get here a list of all the files which have euro dollar tick data here. And then with Vaex, we're going to open all of these files, essentially that have data from, I think, 2008 to 2020. Then we're going to calculate the mid price. We're going to calculate here the spread, essentially. And we're going to calculate the mean and the standard deviation here. So we're not even going to calculate the sum. So this is, I guess, a more complicated operation. And we see it takes 5 seconds here. So we're doing kind of a similar computation compared to Pandas and Dask, yet in spite of that, Vaex is a lot more efficient when it's loading up data. So one thing that you will note with Pandas is a lot of the time is actually spent loading up the Parquet file. So that's kind of what's the slow part. What's here is kind of more clever in the way it manages the loading of the data and the computation. So it's, at least in this use case, it seems a lot quicker to use Vaex. And I've used Vaex in the past when I've needed to work on tick data and I want the thing to compute quite quickly. Obviously, if you're working with a very small data set, potential and relatively simple operations, Pandas are probably sufficient anyway. But this is more when you have very large data sets that potentially you might wish to use Vaex. And we can also use the delayed functionality with Vaex. So this is kind of an example of lazy evaluation that we saw with Dask. So you basically stack a whole number of different operations and it basically optimizes the computation graph for them. And we can see we've speeded it up from 5 seconds here to 3, because doing the mean and the standard deviation and also the count as well, an additional operation, there's a lot of shared computation there, essentially. So it kind of does it more efficiently there. It's also possible to use JIT things with number. We'll talk a bit more about number later on, but maybe I'll skip that. I should probably put this slide after number to explain what number is. Another very popular library, which I haven't talked about, but is kind of gaining popularity, is Polars. This is written in Rust, which is a lot faster than Python. It's got a light Python wrapper on top of that. Instead of NumPy arrays, which Pandas uses by default, it uses arrow arrays. Although I think with the latest version of Pandas, you can actually configure it to use an arrow backend. And typically what you have with Polars compared to Pandas is you have a lot less in terms of data copying, more using views of data. This is also true of Vaex actually as well. A lot more operations are done in parallel with Polars that can take into account, kind of take advantage of like multi-core processors a lot better. Just like with Dask and Vaex, you can work on files that are bigger in memory, concept of lazy evaluation. One of the big differences between Polars and Pandas is that Polars doesn't have the concept of indices, which Pandas has. The syntax, though, is a bit different to Pandas. So it does take a bit of time to get used to. But one area where I've used it quite extensively is to kind of speed up joins. So if you're joining together many different data sets with Pandas, many data frames, it ends up being pretty slow. Whilst with Polars, I've noticed it's quite considerably quicker. But probably the main difference is the syntax is a bit different. So some people argue the syntax is nicer in polars. That might be the case, but I guess if you kind of used to using pandas for many years, it can make it a bit challenging. The next thing I want to talk about is Cython. So essentially, Cython is like a superset of the Python language. So it kind of looks similar to Python, but you can also define, for example, types in it. And what happens is once your code is Cythonized, it can be converted into C, and that can be compiled to machine code. So this is an example of a simple function we have for Cython, for Python, where we're just squaring a number. We're going to load the extension here for Cython. We're going to create two different versions. So this is our original version here. And then here we've added here the double type here. Obviously, this is not going to work with pure Python anymore, by the way, so you put this double type here. And what it's done is Cython has converted this to C code. So if we look at the first version, there's quite a lot of code here, right? So it kind of looks a bit of a mess here. If now instead of that, I also add the type of what's being returned here is double. Once Cython has kind of worked its magic, we see that the amount of C code is substantially less here. And then if we actually do the computation now on these various bits of code, so if we use the original pure Python and use the square there, it's 340 nanoseconds. If we have the one where we put actually the double as the input and define that, it's around 270 nanoseconds. And then we have with a full version where we're also giving the hint as to what the type is of the return of the function, it's around 100 nanoseconds. But I guess one of the things with Cython is you have this compilation step, essentially, this static time compilation step. So number is kind of something that people tend to use a bit more than Cython these days. So it's a just-in-time compiler as opposed to a static compiler for Cython. Number works quite well with NumPy arrays. And you can use number by adding special decorators in your code, and you can use number to target CPU or also GPU as well. One thing to bear in mind is it doesn't necessarily speed up all your Python code and takes some experimentation, but it can be quite effective when it works. So let's just skip this bit. So what I'm going to do is I'm going to just do a moving average with pandas, NumPy, and number and compare the speeds. So first of all, let's load up the data. So this is Eurodollar data for 2019, tick data, so it's high frequency data. I'm going to load that up into memory. If I want to do the moving average in pandas, it's just simply using the rolling window, and I put mean on top of that. So it's fairly easy to do that in pandas. Then I'm going to do the same thing now in NumPy, the underlying NumPy array, do a moving average. And now I'm going to do it in number. So with number, the first thing you notice, I've got this GU vectorized decorator, and I'm putting the types of the inputs and also the outputs here. And also I've written the moving average algorithm from scratch. So it's taken a bit of time to do this, or I guess you can probably Google this and find the algorithm. But I've had to take some time essentially to kind of rewrite it in for loops. But the nice thing with number is that for loops are actually pretty quick. In general, in Python, for loops are slow, but with number, they end up being pretty fast, actually. Okay, so let's run the various implementations of the moving averages to compare the speed. So with pandas, it's 600 milliseconds. With NumPy, it's 4 seconds, but I suspect that's because my implementation is not very good. So I'm not gonna blame NumPy for that. But now if we use number, it's 87 milliseconds. So it's quite a considerable speed up using number compared to pandas. Obviously, the downside is I had to spend time rewriting the moving average algorithm. So it wasn't not a free lunch. But if you find a certain bit of your code provides a bottleneck, then potentially might be worth rewriting. Although I wouldn't recommend rewriting all of your code base in number because it's going to be too time consuming. Okay. And the last example, I think I've got a few minutes hopefully left to go over this, is a specific case where I'm looking at the normal cumulative distribution function. And the reason why I'm looking at this is it's used in many areas of finance. So in particular, for example, the Black-Scholes formula for pricing options. So one of the things that I have done in the past a lot is basically back testing trading strategies for FX options. So in that instance, literally, if you're looking at a daily trading strategy, you're revaluing the option every single day. So over a couple of years, you might be basically calling this function many, many thousands of times. And it ends up being one of the slowest bits of the back test because I'm doing it in a loop. So I'm going to use look at the finance pi library, which can be used to price options. And I'm going to take the CDF function from that as a benchmark later on to check the speed. So first of all, I'm just going to use the normal CDF from SciPy. So that's already been implemented. So it's basically the norm function here. And if I use the one from SciPy, it's 93 microseconds there. We're doing the normal CDF. But then if you look at the code for this, we actually find that underneath it's calling this function ndtr as opposed to the norm function. So why don't I just import that function instead of norm? And in that case, it's 759 nanoseconds. It's around 100 times faster. So literally, instead of calling a high level function norm, I'm just gone through the code of SciPy and basically found the lowest level function, which underneath is basically just C code I'm calling. Okay. So what I can do is I can basically take that code and just convert it into Python. Obviously, it's going to be slower, but you'll see why I've done this later on. So I've taken, this is basically the C code here for NDTR. There we go. So I've just rewritten it in Python, basically converted from the C code manually to Python. I guess these days you could just ask ChatGPT to convert the code anyway. But this was just doing it from scratch. But essentially, the code for Python or C looks very similar. The main difference is here, as I'm using this NumPy function. That's a key difference. So here we find it's around 1.6 microseconds. So it's quite a bit slower, which is not surprising because I'm running pure Python code instead of the lower level C code, which is used in SciPy. But what we can do is we can speed this up using numbers. So in this case, rather than using GU vectorize, which we used earlier, which is for speeding up stuff like for loops, I'm just going to use here ngit at the top with a decorator, and I put the fast math thing up here as being true. So if I run that now, that's 240 nanoseconds, actually. So that's much quicker than the pure Python implementation. And if we go back to the C code, that's actually faster than the original C code that we had, which is 760 nanoseconds. Okay. There we go. So it's quite a bit faster. Not as massive speed up as basically calling the lower level function instead of norm doing NDTR, but it's still quite a big speed up. So we were just using the same algorithm for computing the CDF, but we were just executing it in different ways. So trying to rewrite it in pure Python, then putting the JIT command at the top as well. So, but ultimately it was the same calculation underneath. But we could have a different algorithm for computing the CDF. And in Finance Pi, it has a fast approximation of the CDF, which is pretty good to around 6 decimal places. And this is the code here. So you can see it's quite a bit different here from Dominic O'Kane's Finance Pi library. And we can see in this instance, if we look at the pure Python implementation of this, it's 1 microsecond. But then if you want to JIT it, it ends up being 214 nanoseconds. So this different algorithm ends up being quicker actually than the original algorithm. And just to check to make sure that we have the same numbers. There's nothing worse than benchmarking code and finding it's a lot faster, but then your numerical output is totally different. So it kind of negates the whole point of speeding up your code if the numbers are incorrect at the end. So I guess we looked at several different ways of speed up. So one was using lower level calls in SciPy, later translating the code into Python and then JITting it. Also, we compared it to like a different algorithm for doing the CDF as well. I guess the objective is we want to minimize the effort and make it as fast as possible. But as you've seen, I guess it does take a bit of elbow grease to kind of speed up these things. But here's a few prescriptive ideas in terms of what we did. So trying to use a low-level function to access the same calculation. Potentially, if you want to JIT the code, you can't JIT pandas code, by the way. You have to JIT code with NumPy. And one thing to bear in mind with Number is not every single NumPy operation is yet implemented in Number. So not every NumPy operation will necessarily be speeded up by Number. And then once you're happy with your simplified Python code, you can JIT it. Potentially, you might need to add types as well, additional flags. If it's got for loop as well, you might need to use GU, vectorize, and so on. If you want to also target the GPU, you have to rewrite the code further and kind of understand how the code is executed in GPU as well at the same time. I guess you could consider, once the code is parallel, you could use a cluster of machines, maybe AWS Lambdas or equivalent, or maybe just rewrite it all in Rust or C++. That's another consideration. But I guess we're trying to minimize the amount of effort that we use to speed up the code. And I say the key point is that it's always cool to speed up code. Like, okay, someone disagrees with that statement. Someone disagrees with that statement. But try and target the bits of code which are really big bottlenecks. So in this example, I looked at the CDF because that was a massive bottleneck when I was doing the back testing of FX options. It's been called many, many thousands of times. So it was worth the efforts. I went through the code profile, and that seemed to be like the slowest operation. So do bear that in mind. Try and benchmark your code to identify the slowest bit. Yeah, or I guess maybe you can ask ChatGPT as well to help. But my guess is that more very specialized code, ChatGPT might not be as good, and potentially it might speed up things, but then you have to be careful it's not made a mistake in numerical calculation, so it needs a bit of guidance. Yeah, so that's about it. Hopefully, I've not gone over too much, maybe by 5 minutes. Apologies about that, but thanks again, everyone.